Welcome back. So now let us look at how to compute those gradients like practically when you do this. Let us say that we have one sample xi and by the way all the analysis that I will do, I will do it by assuming that we have one data point. See, finally our loss or the objective function had an expectation of log of p theta of x with respect to px. No, see this expectation I will assume that I only have one data point from the data set and only compute log of p theta of x or the lower bound on it. So to do it, I mean to make it compute this expectation, you just have to take all the samples and put another summation over all data points. That is not how is it done in practice. The way we do it is that if we are given 1000 data points, we take, you know, the batch processing idea, right? We take batches and we compute this on every batch and we do it on the entire data set, and that is called one epoch, and we do it on multiple epochs. That is how it is done in practice. Okay, but from now on every computation that we do, I will show it only for one single data point, because otherwise I will have to put another sum over all data points for each case. I will just skip that for the ease of writing. Fine. So let us say that we have one data point in RD xi, we have this neural network which is the encoder. Now we initialize randomly this phi and pass this xi through this encoder network to get a mu phi of xi and sigma phi of xi. I mean, all I am saying is that we interpret the outcomes of this neural network as mu phi of xi and sigma phi of xi, that is it. Then we get two vectors, interpret them as mu phi of xi and sigma phi of xi, right. Then what do? Then you sample a data point epsilon I from normal 0 1. See, this sampling is outside of the neural network, this has nothing to do with neural network, you sample it outside. Then find a zi by reparameterizing it. So take that epsilon I, which is the sample from the normal distribution that you have gotten, and pass it through the affine transformation, which is take the output of the neural network, multiply this epsilon I with the sigma of xi, and then shift it through mu I, and that gives you a zi. Make sense? Okay. Then pass that zi through the p theta network, okay, to get what? To get either the parameters of p theta of x given z or the samples of p theta of x given z, as the case may be. If you want to see this neural network as a deterministic one, then it is giving you samples of p theta of x given z. If you want to look into it as a probabilistic neural network, then it is giving you the parameters of distribution p theta of x given z. Okay, we will come to that in a while, but take that zi, pass it through this p theta of x given z network, you get the parameters of p theta of x given z. So that is one forward pass starting from xi. Is this all right? Is this clear? Okay. Once we have it, then we have to compute this thing, no, which is what our gradient is. Now the gradient of expected value of log of p theta of x given z now is gradient of expected value of log of p theta of x given g of epsilon, because my z is now g of epsilon. We have computed this, and now this expectation can be approximated using law of large numbers, where the samples are the samples of epsilon, not the samples of z. Do you see this? Because the expectation is with respect to p epsilon now. You understand? So now what is happening is that for the same xi, we sample multiple epsilons, and every time we get an epsilon, we get a zi, pass all those zi's through the decoder network, okay, to compute log of p theta of x given g of epsilon j, and then you compute this sum. Please note that this sum is not over data points, it is over the multiple samples that we have done from the auxiliary distribution epsilon. You see this, and we do this for a single data point, and if you have to repeat this procedure on the data set, you have another summation over the batches of the data as well, which I am not writing. Only even for the single data point, pass one data point through the encoder, sample multiple times the epsilon, because for the law of large numbers to go, you will have to ensure that this expectation is well represented using multiple data points. Typically this m is taken to be some 8, 10, 16 or anything. Worst case, you can also take m to be 1, where you only take one zi for a particular xi, that is also fine, which is a single sample estimate of epsilon, and it is only as good as it can be. Okay. Do you understand what this is? See, there is one missing piece. I have still not told you how to compute log of p theta x given g epsilon. I will tell you that in a while. Assume that this somehow we get this at the output of the decoder network, okay, and I will tell you how to compute this in a while. But is this expression clear so far? What's happening? Any questions here? Yes. Which distribution? Q or P? Sure. Hold on to that question. The question is, if we make our decoder probabilistic in the sense that we are predicting the parameters of p theta of x given zi, what would our training data look like? It's a good question, just hold on to that. Okay, I will answer that. Anything else? Yeah.
So would it also make sense to approximate the summation by sampling from, but basically doing it in an iterative approach in terms of phi. So based on the earlier phi of t, I sample and then update phi of t plus 1.
To get epsilon, you are saying?
Instead of epsilon, why can't I use the previous iteration
of the encoder itself to sample what? To sample different mu's.
here? No,
See, the point is, the expectation here is with respect to that auxiliary random variable which has been used to reparameterize. Now, you need more samples from p epsilon. How do you get it? If you take the previous iterations of the encoder phi itself, you will not get multiple samples of from the epsilon. See, why are we doing multiple sampling multiple times is that we have an expectation with respect to p epsilon, and to approximate this expectation well, we need multiple samples from epsilon, or rather p epsilon. How do we do that? We sample multiple times from the distribution p epsilon, which happens to be normal distribution in this case.
So I'm saying instead of sampling from p epsilon, would it make sense to sample from q of phi p minus 1?
How do you sample from q of phi? It is only through epsilon, right, because you have reparameterized. The only quote unquote randomness is coming from epsilon here. That is the whole point of reparameterization. I have designated the randomness from phi to epsilon. So, the only source of randomness is epsilon now. That is why you need to sample multiple times from it. See, unless what you are saying, I mean, I thought that is what you are hinting to. If you want to see phi itself as a random variable, right, and treat every iterate of phi as one sample from the space of parameters and see this as a Bayesian neural network, that is a different idea altogether. But we are not looking at that. So, we are only looking at treating phi as a deterministic variable here. We are not looking at Bayesian belief nets here. Any other? Yeah.
So to get mu phi and sigma phi itself, you need to sample multiple times. Because how will you find mu phi and sigma phi itself?
No. See, the question is, do we need to sample multiple times to get mu phi and sigma phi? No. See, mu phi and sigma phi are outputs of this neural network, which is deterministic. So, given an xi, it will give you one mu and one sigma. That is not going to change. Hold on. What is going to change is zi. That will change. What will not change is mu and sigma.
I thought mu phi and sigma phi, somehow we are calculating from the samples itself. Like we are just getting samples and somehow we are.
No, there is no somehow. I mean, it is very well defined. So, xi is the input, the output of the neural network is mu and sigma, which is not going to change.
Neural network will output these parameters also.
Neural network will only output these parameters and nothing else. See, that is the whole point of probabilistic neural networks. Neural network will output two vectors. That first vector is my mu, second vector is my sigma. That is not going to change. That is how I have built my neural network.
So this is not generating samples, this is generating distribution, parameters of the distribution itself.
Precisely the point. So, that is the way of, I mean, that is why I started this class by saying that there are two ways of representing distributions. One is that the neural network will give you parameters, the other is the neural network will give you samples. Here the neural network is not giving you samples, it is giving you the parameters of the distribution. So, which is, and neural network is a deterministic function, which means that given a particular input, it is always going to give you a particular output, correct. That is why mu and sigma are fixed for a particular x, okay. Anything else? So, this is often confused, because perhaps this is the first time like that you are encountering a neural network which is giving you samples of distributions, right. So, that is a bit of surprise. We would have actually seen this, but not realized that this is what is happening, right. So, that is why I spent some time. This neural network, which is the encoder in a VAE, is always giving you the parameters of the posterior distribution, not the samples. Okay. Now, the next question is, how do we compute log of p theta x given z, right, which is g of epsilon j in this case. He was asking, no, how do we compute this? Okay. One way to do it is, not the only way, one way to do it is, now our decoder is also probabilistic. Assume that decoder is also probabilistic. If you assume that it is giving you the samples of that distribution, I will tell you how to do it. So, for now we assume that it is a deterministic, it is a probabilistic neural network, it is giving you samples. Now, the moment you say that it is a probabilistic neural network, you will have to assume a distribution on p theta of x given z, assume that it has some known distribution. Now, let us say that we assume that it is Gaussian. This is again one assumption that I am making, you can make any distributional assumption on the distribution. Let us say that it is Gaussian. Now, look at my notation here. My notation is that it is a Gaussian distribution on the random variable x. Why? Because it is sampling from p theta of x given z. This is a distribution on x, therefore, it is a distribution on the random variable x. Now, these are the parameters. What are the parameters? The mean of this distribution, okay, is the output of the neural network. That is what I am representing as x cap theta of z. Why is it a function of z? Because it is a conditional distribution and this neural network is taking a fixed z as an input, okay, and the output of this neural network now is the mean of this distribution, and I deliberately assume that the variance of this distribution is identity. Fine. If I make that assumption, then log of p theta of x given z looks like this. It is log of 1 by 2 pi d by 2 e power minus the quadratic form x minus the mean whole squared. There is no the sigma goes away here because it is, I have assumed that to be an identity. Fine. Okay. Now, this let us leave all the constant terms out. What is this term? This is mean squared error. Now, if you assume your distribution to be a Gaussian, I have said this in the previous course also, right. If you assume to be your distribution to be Gaussian with the identity as the mean, then the conditional distribution or the log likelihood would turn out to be a mean squared error loss, that is it. So, now what is the data that is needed? It is still x, but what you compute at the output is the mean squared error. So, you take x for that particular xi, take the output of the decoder and measure this distance, and that is your log likelihood. Make sense? Now, hold on. Now, suppose you assume this distribution to be, let us say, Bernoulli, right. What would be the loss be? What would be the log likelihood would look like if you assume this distribution to be Bernoulli? Of course, this is a vector. I will assume it to be Bernoulli at each dimensions with independence. What would that loss be? Cross entropy. Do the algebra and see. We have done this in the PRNN course, right. So, if you assume this to be a Bernoulli, and what is the output of the neural network then? Every neuron of the output of the decoder is giving you that parameter of that Bernoulli distribution, which is the probability of that particular pixel being white. If you model it that way, then this will be cross entropy. So now if we flip the story and say that I will choose mean squared error as my loss function in a VAE, I am implicitly saying that I have taken my decoder to be probabilistic and I have assumed my conditional distribution to be normal with the mean of that distribution to be the output of the decoder. That is all I am saying. A VAE with a mean squared error loss at the output is a model which has made an assumption that the decoder is probabilistic with the output of the decoder giving you the mean of the distribution with Gaussian. They are equivalent. Do you realize this? Yeah, that is it. Yeah. Okay. So this is that equivalence that we were looking at the previous course, right? There is whatever we do in the probabilistic sense has a ERM equivalence, empirical risk minimization equivalence. We can see that everywhere. Okay. So now this entire term now under these assumptions, let me complete this. Under this assumption, this entire term will look like this. The gradient term, no, the gradient of the expectation of the conditional log likelihood with respect to Q will simply look like this. The gradient of this thing, yeah, mean squared error with respect to phi. Now there is theta here. Theta is the decoder parameter. Where is phi? See, this is the gradient with respect to phi. Where is phi coming up here? In z, because z is mu phi of xi plus sigma phi of xi and therefore it becomes a function of phi. Is that all right? Now here is how I still have to stop for questions. I will do this entire this is one forward pass and backward pass and then I will ask stop for questions. Now how do you train the encoder of a VAE? Given a data point xi, okay, pass it through the encoder. This is one forward pass. Get your mu phi and sigma phi. Now using this is okay. Stop there. Sample m epsilons from normal 0 1 and compute the corresponding z's through reparameterization. Okay. Now pass all those z's through the decoder and compute the output, the mean of the decoder or the output of the decoder at all zj's. Then compute this mean squared error. So for all zj's, no, compute this xi minus x cap theta zj, compute the squared error, sum them up over all zj's and then back propagate that all the way through the encoder. That is it, by keeping the decoder parameters a constant. Now there is one nuance here. When you are back propagating, right, when you come to the first layer of the decoder, you will have to back propagate through this operation as well. See, gradients that you get here with respect to phi have to be back propagated through this operation as well. So you have to treat this as another layer in the neural network. Get what I am saying? So to take the gradients of this with respect to mu phi as well and then you back propagate all the way through the encoder, and this is one backward pass through the encoder and then you do this one step. You get this, right? Once you get this, then you do phi t plus 1 is equal to phi t minus the gradient of that elbow divided gradient of this elbow with respect to phi t plus 1, update it with phi t minus alpha times gradient of j with respect to phi, that is it, which you have computed. In fact, you have only computed the gradient or the first term of the objective function, the second term still remains. I will tell you how to do that. Okay, but yeah, so thus we obtain the gradient of this expected log likelihood with respect to with respect to phi. Okay, now I will stop. Is this clear? So this is the hard part. The rest of the things is all algebra. It's very easy. This is the only like involved part in training a VAE. Any questions here so far? Is it already answered? Whatever question you had, or? It is not, see, in that world view, no, it is not outputting the samples, it is giving you the mean of this distribution. Yeah, but then they are not the samples.
But
If you want to interpret it that way, it's fine. No, it doesn't matter. See, if you want to interpret it that way, you can interpret it that way. So let's take the generator of Gyan for instance. Can you interpret that as something that is giving you the mean of a distribution? It's giving you the sample of a particular distribution, right? It's left to the designer, and if you want to interpret it that way, you can interpret it that way. Here, if you interpret the output of the decoder as the mean of that distribution, right, then the conditional log likelihood will turn out to be squared error loss. See, do you see what's happening here? What's happening here is, if you take a particular data sample, data points, let's say that you are taking one digit in MNIST, pass it through the encoder. See, for the same data point, remember one of our objectives in the latent variable models is that we get an embedding corresponding to each of the input data points, correct? Here we are not getting one embedding vector, we are getting an entire distribution given a particular data point. What is the distribution? See, what is q phi of z given xi or x equal to xi here? It is a Gaussian distribution with mean mu phi, variance sigma phi. So now for a single data point, you are getting an entire distribution as embedding, right? Now what the decoder is doing is that as long as I am sampling from the embedding corresponding to that data point. What is the Zi, by the way? Zi are several embeddings for the exact same data point that I am getting from the encoder. For a single data point, I am getting several embeddings. Do you see why? Every Zj that I am sampling is actually one possible embedding for my Xi, and there is no single embedding. There are infinite embeddings that we can get because we have a distribution corresponding to a single data point, input data point. Now what am I asking my decoder to do? I am saying no matter what Zi you are seeing as an input, give me the exact same output, okay, that corresponds to this Xi. So I am trying to say that the Xi that I have, okay, is actually the mean image of multiple images that can cluster around that one particular image. That is what I am trying to say here. And multiple embeddings that I am getting at the encoder is actually the embedding corresponding to several images that have cluster around this single image, which is what the decoder is trying to recover. You see the story? So that is why for a single image you are not getting a single embedding, you are getting an entire distribution around the single image as an embedding. See, this is not the case in let us say like BiGAN. The encoder of the BiGAN will not give you a distribution, it will give you a single sample corresponding to Xi. Here you are not getting a single sample, you are getting an entire distribution around a single image, okay, that is what is happening. Any questions here? Yeah. Good observation. The question is, wouldn't the predicted image or the predicted mean, so you want to see this as an image, you can see this as an image, whatever is predicted, wouldn't it be blurry? Because you are looking at an average of multiple images, this is a known drawback of VAE. It is going to be blurry because you are looking at an average image, so to speak, right? You are taking an expected, you are taking multiple embeddings for a given image, no, it is going to be blurry, and it is a known drawback of VAE. People have asked, how do you solve this problem? So, there is, we will see this, there is actually, there is more to that problem that you say, there is something called posterior collapse, which we will see, and there are, people have come up with ways to deal with this posterior collapse, which we will eventually look at. Yeah. It will be.
But if we are outputting a x theta zi, which is the mean of the decoder, so are we actually projecting it to that big of a space of as similar to as the image?
We should know, because otherwise there will be a dimensionality mismatch here,
yeah.
And this distribution p theta of x given z is a distribution over x, which means that its dimension should be RD, which is the ambient dimension.
Okay.
See, that is why you have this auto encoder idea also, no? This Q, which is the conditional variational posterior, is taking an image and embedding it onto a space. The decoder is taking that embedding and projecting back onto the data space. In fact, we will see later that at the end of the day, or rather we have to make this also a generative model, right? Where is it generating images from? We will use the decoder as sampler. It is projecting back onto the ambient space. So, one interpretation that people give is that what is this encoder doing is it is trying to model that manifold. This manifold is effectively of a lower dimension. Now, it is trying to model that manifold using the encoder. If you have done it well, then you can recover the data back in the ambient space using the decoder is the idea. Okay. Fine. So, now we will go to the easy parts. I have to compute the second term in the elbow, which is the KL divergence between the variational posterior and the prior on the latent variable. Now, you assume some deterministic form on the latent prior as well. So, this is one way to solve this problem, make it independent of theta. Now, you can question this assumption, why should be the prior on z should be assumed to be normal 0 1. It need not be assumed. In fact, I mean, I myself have a lot of work around what should be the optimal p theta on z, p theta of z in a VAE, so that you get the optimal performance. Okay. But anyway, so one easiest way to do it is assume that to be normal 0 1. Now, if you do that, this KL, which is the second term in elbow, will be a KL divergence between two Gaussian distributions, no? Because Q phi of z given x is a Gaussian distribution with mean mu phi and sigma phi. The p theta of z is a Gaussian distribution with 0 mean and unit variance, correct. Now, this KL divergence will now be a KL divergence between two Gaussian distributions, and the KL divergence between two Gaussian distributions can be deterministically computed. Take it as a homework and do it. Show that KL divergence between two Gaussian distributions can be written using this particular formula. It will be a function of the means and the variances. You have to compute the trace of those particular matrices. Just do it, I mean, it is easy. Now, since this can be estimated, gradient with respect to gradient of this with respect to phi can be easily found out. Okay. Now, how do you do that? Same thing, right? You do a forward pass. When you are doing the reverse pass, just before you push the gradients through the encoder, you also compute the gradient of the scale term with respect to phi. And this is a deterministic thing. It has to be computed at the output of the encoder, right? Why? Because this scale is a function of mu and sigma. So, the gradients, there are two terms in elbow. The first term is this reconstruction term, which has to be computed at the output of the decoder. You compute there and then back propagate. And the second term, which is the KL, has to be computed at the output of the encoder, right. So, you add the gradients of that KL term also while you are at the output of the encoder, and then you back propagate, that is it. Gradients are additive, no, they can be added at any point. So, you add it at there. I mean, you can compute it here as well, but anyway, I mean, you can, they are constants with respect to theta, so you can just back propagate it that way. Are we good? So, this completes the training of encoder, and there is a plus here because we are trying to maximize the elbow, no. It is not a gradient minimization problem, it is a maximization problem, and that is why there is a plus here. There is one training step for encoder, that is how you do it. Are we good? One single data point, one training step through the encoder. Okay. Since I am not writing, it is going too fast and I am talking continuously. I need to break it. It is okay, we can continue. Is it going too fast? See, I told you the intention, right? We'll run through all this quickly. It's fine, let it be there. Nothing of the world. We can run through all this pretty quickly, and then we'll cover more ground. I'll write those parts whatever I'm doing afresh. From the last year, I'll write those parts. Okay. Let me know if it's faster, then I can actually go a little slower as well. That's no problem. Okay, so once we are done with training the encoder, we'll have to now train the decoder, because the latent variable model has optimization both with respect to phi and theta. We'll have to optimize with respect to theta. How do we do that? The second KL term is independent of theta, and it will just go away, because it has no dependence on the decoder parameters. It will simply go to 0. Scale is between q phi of z given x and pz, right? And if you take the gradient of that with respect to theta, it will just go away. The first term is dependent on theta because you have the decoder term here. How do we do that? It's pretty simple. Take a data point xi, do one forward pass through the encoder, get your mu and sigma, sample multiple epsilons, get multiple z's, okay, and then pass them through the decoder, compute the log likelihood term, then just back propagate that term with respect to theta in the decoder. That's it. You don't have to touch the encoder. You need encoder to get your embeddings or the latent variables to give as an input to the decoder. Once you do that, just compute the log likelihood at the output and back propagate with respect to theta. That's it. This is one step through gradient through the decoder. This is one data point, one gradient step through the encoder and decoder. Do it over multiple data points in the batch processing way, and you can do it over multiple epochs as well. That's how it is trained. Okay. Yeah, this is summary of how VAE does. Let's run through that. So we are given n data points from the data set, unknown distribution. We have an encoder and a decoder. Both are probabilistic. Now to ease things out, you assume the distribution of q of z given x to be Gaussian with diagonal variance, okay, in which case the output dimensions of the encoder will be 2k, k for mean and k for variance of the diagonal. So the input dimension is d because it takes a data point as an input. In fact, you can take your favorite neural network and you can make your encoder to be a CNN, can be an RNN transform or whatever your favorite neural network is. Right? Same thing with the decoder. You just have to some neural network. All that you need to ensure is that the output dimensions match. That's it, right? And then we have a decoder which takes a k dimensional latent variable as input. Please note that the decoder takes the latent variable as the input, an instantiation of latent variable as an input. And how do you get it? Where do you get it from? You get it through sampling and reparameterization. Sample, see, this is what people mean when they say that you cannot back propagate through sampling. See, when they write blocks, they say that in a VAE you need reparameterization because you cannot back propagate through sampling. What are they trying to say? They are trying to say that here is an expectation, and this expectation is with respect to q, and you need to approximate this expectation with respect using law of large numbers, using samples from q, and the sampling has to be done. Okay, and you cannot back propagate through sampling because sampling is a non-differentiable operation. Now you understand what it means, right? Write this expectation, you have that integral is approximated using sample averages, and there is that sampling which is not a differentiable operation. Therefore you need to decouple the sampling operation from neural networks and reparameterize it. That's all it is. Okay. So now what happens is that you do this, you do that sampling outside of the neural network, reparameterize and give it as an input to the decoder, and whatever you get at the output of the decoder, treat it as the parameter of the distribution p theta of x given z. Once you do that, all the terms are computable. Do one forward pass and compute those terms and back propagate through the encoder and decoder. That's how you train a VAE. Okay. This is one instantiation, right, where we assume those to be Gaussian distribution. This is how see, if I ask you to code up VAE, what you code up is this. there are two neural networks and these terms are what you will code up, and of course there is a sampling step outside of it, and then you simply back propagate, that is it. Treat that reparameterization step as one layer in your entire neural network, right. So, there is encoder, reparameterization, decoder, but they are not connected. You need to write, if you know how to write neural networks in PyTorch, you need to write two forward functions, right, two different classes of neural networks, and then two forward functions to ensure that these things are passing, gradients are passing correctly, right. And theta and phi are updated alternatively via gradient descent. That's usual neural network training stuff. Okay. Okay. So now once we train the neural network, good point to stop. Okay. Once we train the neural network, how do we infer? We will have to use it for inference, right? We can use neural networks, I mean VAEs, sorry, once we train VAEs. Okay, by the way, they are called variational autoencoders. I have not told you why. They are called autoencoders because in this instantiation you can look at this first term as the reconstruction term. So, there is an encoder, there is a decoder. The encoder is giving you embeddings and the decoder is taking embeddings and reconstructing the data back, and the cost that we are incurring is that of reproducing the data point back, and that is why it is auto encoding. So, it is encoding itself, that is why it is auto encoder. Variational because we have used the variational distribution and variational calculus and optimized with respect to Q by constructing the elbow, that is why variational, that is why the name variational auto encoder. The paper's title is auto encoding variational Bayes. Why? It is auto encoding variational. Why? Where is Bayes coming from here? It is because we are trying to find the posterior of the latent variable given the data using the priors, or rather the other conditionals P of x given C. Okay. So, with this, no, I would suggest all of you go back and read the original VAE paper. It's fun to read. It's a very nicely written paper. Please read it. Okay. And I told you, right, every algorithm or every model that we see in this course, once we complete it, I suggest that all of you go back and read the original paper. Same thing with the F divergence minimization and this as well. So, your evaluation, exam, etc. would have questions or rather ideas which are discussed in that paper, things that similar, especially read the appendix of those papers. A lot of proofs are deliberated to appendix, right. So, you have to read the paper in its entirety. Okay. With this background, I think now you can read. Once it is done, no, you can go back and read those papers. Any questions? Yeah, you had a question. That is what is happening, no? Well, you can, but I don't know what do you mean by turning them simultaneously. No, but while you are back propagating or rather while you are updating the encoder parameters, you assume theta to be constant, no, just like in EM. In EM, you assume that for a given theta, see when we constructed elbow, the question that we asked is for a fixed theta, what is the optimal phi? And for a fixed phi, what is the optimal theta? And we alternate between these two. Just like in EM, yeah, just like in EM. So, this encoder decoder training in a VAE is similar to the expectation and maximization steps in EM, because it is a latent variable model that we are doing. In fact, k-means, that is exactly what we do, right. In k-means, we assign data points to different clusters. So, that is your maximization step, and then you recompute the cluster centers, that is your expectation step, and you keep alternating between these two, right. K-means, I mean, have you ever imagined that running a k-means algorithm is similar to training a VAE? They are actually same, I mean, or rather similar in the essence that they are both latent variable models trying to find the latent posterior and the model parameters alternatively. Yeah. So, once you train a VAE, how do you use it for inference? You can use it in multiple ways. One, for data generation or sampling. Okay, how do you sample from a latent variable model in general is as follows. So, we know that the latent variable model is defined as the marginal bit of the joint distribution between these two, right. Now, how do you sample from in a latent variable model is that you sample from the conditional distribution of data given the latent variable. How? First sample from the latent variable, the marginal of the latent variable, get a z nu from pz. What is pz? We know that pz is normal 0 1, right, that is what we have assumed. So, get it from it and then sample the new data point from p theta of x given z. How do we sample from p theta of x given z? Here in this case, we know that it is a Gaussian, okay, and I know how to sample from a Gaussian, but what is the unknown here? The mean. How do we get the mean? Decoder. So, get this z nu, okay, pass it through the decoder, which will give you the mean of p theta of x given z, and then sample using that mean, sample from the Gaussian. Or if your decoder is giving you the samples of p theta of z given x, sorry, x given z, then the output of your decoder itself is the sample that you display as the generated sample, that is it, depending upon how do you model it. Or in some cases, even if it's a probabilistic case, right, you can take the mean itself as the image that you want to use as the generated image, that is also fine, okay. We have assumed, no, that is what we have assumed, no. You see, here I think you missed it. When we are computing the KL, we assume the latent prior to be normal 0 1. See, now one question is, right, see, this decoder was trained to give you the mean of p theta of x given z by taking the samples of q phi of z given x as input. Now, how are we getting the mean of p theta of x given z when the decoder is shown the samples of normal 0 1? Do you see the question? How was the decoder trained? The decoder was trained to give you the mean of p theta of x given z by taking samples of q phi of z given x as input. That is how we trained it. Now, during inference we are asking it to give me the mean of that distribution by taking samples of normal 0 1 as input. How? Exactly. See, what we have done is in the second term of the VAE, while we have trained, we have ensured that q phi of z given x for every x is going close to normal 0 1 by minimizing the KL. What is the second term in elbow? The second term in elbow is this, is the KL divergence between q phi of z given x and PC. If we have trained this well, then for every x q phi of z given x, or rather for every x, this neural network is giving you 0 and 1 as output. This encoder neural network is giving you 0 and 1 as output, is what we have asked that encoder neural network to do. Isn't this an issue? This is what is called as posterior collapse, which we will discuss in the next class. But anyway, so since this decoder is now, encoder is trying to make q phi of z given x to be normal 0 1 for every x, decoder has learned to take samples from normal 0 1 and give you the mean of p theta of x given z. That is why it works during inference, or it should work during inference. So, this is how you generate. Now, you can use so I already told you, either use the mean as the novel generated data point, or you sample from that normal distribution by taking this as a mean and use that as the novel generated data point. You can do both of it, okay. Now, for posterior inference or embedding or feature extraction, how do you use it? The VAE, it is now obvious, no? Given a data point x, pass it through the encoder and you get mu phi and sigma phi. Use that to sample from that Gaussian distribution, and you can take any sample from that distribution as your embedding corresponding to xi, or you can use the mean itself as the embedding and use it for whatever purpose that you would want to use. Are we good? Okay, so that is about VAE. Now, as I said, the problem is that this encoder is encouraging, this KL term is encouraging the encoder to make q phi of z given x to be normal 0 1 or rather pz for all x. So, which means that no matter what input I give, this neural network is asked to give 1 and 0 as output, right. Isn't it an issue? I think it's, I mean it seems to be an issue, and this is what is called as posterior collapse in a VAE, and there are ways to tackle that problem, okay, which we will see in the next class. Okay. So, that is it for today. Thank you.